Swayam Prabha. Digital India. Educated India.
Namaskar. So, today we will start our discussion on state variable analysis, and particularly in this session we will discuss about the graphical model of the system. So, let us try to understand what are the various graphical models used in the control systems. So, basically the graphical model is nothing but the pictorial representation of the system. Generally we take only the linear system for the presentation. For example, if you see the figure shown in the slide, it is a graphical representation of the system which has one input and the output, and in between you have the mathematical representation of the system. So, generally we use two different types of graphical models, one is block diagram and another is signal flow graph. So, now let us first understand what is block diagram. So, block diagram is an interconnection of symbols representing certain basic mathematical operations in such a way that the overall diagram obeys the system's mathematical model. So, if you see this particular block diagram, you have US as an input and YS as an output, and inside you have the set of blocks which when you represent them mathematically will give the complete systems model. So, in the block diagram we use the Laplace transform of various quantities, whether these are signals or the processing blocks. We use the Laplace transform to represent the systems model in block diagrams. So, the operations used in block diagram can be the summations or maybe gain or multiplication by a transfer function. Say for example, in this case if you see this particular symbol is for summation, where you have the various signals summed up. So, here you have US as an added signal and ZS is negated. So, US minus ZS is the output which you will see as Vs, and then the mathematical representation of the transfer function, that is Gs you will have, and then you have the Ys. So, you will see different elements in this particular block diagram, and we will discuss the different elements which we will see in the block diagram one by one. First, let us try to understand what is summer. Summer means the addition and subtraction of variables. So, when you want to add or subtract the variables, you represent them by a summer, or you can also call it as summing junction. So, if you see this particular figure, you will see one summing block you have, where you have multiple inputs coming and then you have one unique output, that is Ys. So, the summer is represented by a circle. If you see this figure, it is represented by a circle and number of arrows directed towards it, which are nothing but the input for the summer, and one single arrow which is nothing but the output of the summer. So, here if you see the inputs are x1, x2 and x3, and in each and every arrow you will see this plus or minus sign is presented, which indicates whether you want to summing up or you want to subtract the signal. So, if you see this particular figure, you have two inputs as a summation and one as a subtraction. So, Ys would be nothing but x1x plus x2s minus x3s. So, the output variable appearing as one arrow leaving the circle is defined as the total sum of the incoming variable. So, y(s) will be the total sum, that is x1 plus x2 minus x3. So, summer is basically used for either adding or subtracting the variables. Now, let us talk about the gain block. The multiplication of a single variable by a constant is represented by the gain block. There is no restriction on the value of the gain. So, it can be either positive or negative, or it can be a algebraic function of other constants and or system parameters. So, if you see this particular block, A is the gain block. So, the y(s) will be A into x(s) in this case. So, if you take the particular value of A, say minus 5, then y(s) will become minus of 5 into x(s). At the same time, you can represent the block as a as an algebraical function. So, like in this case we have represented this gain as k by m. K and m are two different variables. So, if you put the values of k and m, you will get the total gain which you will get from this block. So, y(s) will become now k by m into x(s). So, gain block is basically used to amplify the signal input. Now, let us talk about the transfer function. This transfer function concept we have already discussed when we were discussing about the Laplace transform. So, let us recap what we discussed at that time. So, for a fixed linear system with no initial stored energy, the transfer function, that is transformed output, that is y(s), can be given by y(s) equal to h(s) into u(s), where h(s) is the transfer function of the system and u(s) is the transformed input represented in Laplace domain. Now, when dealing with the parts of the large system, we may use subsystem Laplace transform. So, Fs is the Laplace transform subsystem, that is basically the part of a larger system, and Xs is the input for that subsystem. In that case, the intermediate output, that is y(s), can be represented as Fs into Xs. Now, how you will represent? You will represent this particular equation in the form of block diagram, as Xs is the input to the block, Fs is the transfer function and the y(s) is the output. So, y(s) will become Fs into Xs. Now, if we have a first order system, then in that case the first order system can be represented by the Laplace transform. So, transfer function for the first order system will become some constant A divided by s plus 1 upon tau. So, this will be the transfer function for a typical first order system, and if you are asked to represent it in the form of block diagram, so you will give Xs as an input to the block. In the block you will have the transfer function of the system, that is A upon s plus 1 upon tau, and y(s) will be the output. So, y(s) can be represented as A into A divided by s plus 1 upon tau into Xs. Now, let us talk about the integrator block. So, if you recall, we discussed about the integration related when we were discussing about the Laplace transform. So, we use that discussion in this particular analysis, where we want to find out the transfer function of the integrator block. So, in that case, if you consider x t as an input and y t as an output, so the y t is the integration of x t. What we can write? Y t is equal to y 0, that is the initial condition, plus the integration of input signal x t. So, what we can write? Integration between 0 to t between 0 to t x lambda d lambda. So, this lambda is the dummy variable to find out the integration of the input function x t. Now, if you consider y 0 equal to 0, that is initially the system does not have any value. So, you can simply write y t is equal to 0 to t x lambda d lambda. Now, if you convert into Laplace domain, yt can be simply written as ys, and the integration term you can write as 1 upon s into xs. So, this is what we discussed when we discussed the Laplace transform for the integral term in the previous lectures. So, we can write ys now as equal to 1 by s into xs. When you are asked to find the transfer function, that means you need to find out ys upon xs. So, ys upon xs will become 1 by s in case of integrator. Now, when you are asked to draw the block diagram, you can simply write xs as an input to the block. Within the block you will have integrator, the Laplace transform of the integrator, or you can say the transfer function related to integrator, that will be 1 by s into ys. So, the ys you can simply get from the block diagram as 1 by s into xs. Now, there are the blocks which may be in series combinations. Now, when you say that the blocks are in series combination, it means that the blocks, the output of one block will go to other block as an input, then we will say that the two blocks are in series. So, you can see in the figure, the xs is the input to the block having transfer function f1s. So, the intermediate output is Vs for this particular block. So, this output goes directly as an input to the another block, that is f2s, and then finally you get the ys. So, f1, the transfer function will be Vs upon xs, and f2s, the transfer function of second block, will be ys upon Vs. So, if you use these two equations and simplify, you can say that ys upon xs is nothing but f1s into f2s. So, when two blocks are in series, so you can combine both of them and represent by one single block, and then the block will be f1s into f2s. So, x1 is the input, xs is the input, and f1s into f2s is the combined transfer function of the system, and ys you will get as an output. So, in case of series combination, you can multiply the transfer functions and get the final transfer function of the system. Now, if the blocks are in parallel combination, means two systems are said to be in parallel when they have common input and their output are combined by a summing junction. So, if you see this figure, here f1s and f2s are the two subsystems. The transfer functions of these two subsystems are f1s and f2s, and these two systems are given the same input, that is xs. So, you will get the output V1s will correspond to the transfer function f1s, and V2s is for the transfer function f2s, and when you sum up, you get the ys as V1s plus V2s. So, in that case, if you sum up, you will get ys upon xs, that is output by input, as the sum of two Laplace transform. So, Laplace transform of system S and basically the transfer function of system 1 and transfer function of system 2. So, you can, when you are having the parallel combination of the two subsystems, the combined transfer function will be f1s plus f2s. So, you can represent this with the equivalent block diagram as xs will be the input and the transfer function of the combined system is f1s plus f2s, and ys will be the output. Now, let us talk about the block diagram of the feedback system. So, this is basically a typical the block diagram of the system having one feedback loop. So, us is the input and zs is the output of the feedback loop. So, vs you can simply see as us minus zs, and this goes into the transfer function gs, and you get the output as ys. So, in this case the system has one feedback loop also. So, we will see what are the various components we have in this particular block diagram. So, Laplace transform for the system's input and output are as us and ys. The transfer function gs you can find out as ys upon vs, which is called as forward transfer function. So, gs is called as forward transfer function, while in case of hs, that is the transfer function for the feedback loop, you will have hs as zs upon ys. So, this particular transfer function is called feedback transfer function. When you combine gs into hs, you get another term called open loop transfer function. So, these three are the most important transfer functions which we use frequently to represent the feedback system. Now, given the model of the feedback system in terms of its forward and backward transfer function, we can determine the transfer function of the complete closed loop system. So, we can say we can determine the closed loop transfer function. The closed loop transfer function will be given as, say, the total output is T s. So, you can write the T s is nothing but the transfer function of the complete system will be y s, that is the output divided by input. So, we need to find out the value of T s. T s is, we can find out the value of T s by putting the value of y s and u s. How we will put the y s value of y s and u s? We take the help of the figure which we see in this slide. So, first we find the value of V s. V s is nothing but u s minus z s. What is z s? Z s is y s into h s, and what is y s? Y s is g s into V s. So, we have these three equations. First is V s is equal to u s minus z s, y s as g s into V s, and z s is h s into y s. Now, with the help of these three equations, we will eliminate V s and z s. So, when we eliminate, we get the value of y s as g s into, in place of we put the value of V s, we put the value as u s minus z s. So, we put u s minus z s, and in case of z s we put the value of h s into y s. So, we get now y s as g s, in bracket you will have u s minus h s y s. Now, if you rearrange, you can write y s into 1 plus g s h s equal to g s into u s. So, the closed loop transfer function T s, so that is the transfer function of the complete system will be y s upon u s. So, when you put the value of y s and u s, you get the transfer function T s as g s upon 1 plus g s h s. So, the figure which you saw in this particular case, so if you take the complete system and see the transfer function of the system, this transfer function will become T s. So, you can equivalently represent this system as the simple block having the transfer function of the feedback system, that is g s upon 1 plus g s h s, and the u s is the input and y s is the output. Now, here in this case we say that in the previous figure we can observe that the summing junction will have negative feedback signal. So, here we have added negative as a feedback signal to find the Laplace transform of the complete feedback system. Now, let us talk about another, the graphical representation of the system, that is signal flow graph. So, signal flow graphs are also an alternative system representation. Unlike the block diagram which we discussed for the linear system, which consists of blocks, signals and summing junctions, in case of signal flow graph we will see for the linear system we will see only branches which represent the system and the nodes which represent the signals. So, if you see the branch, if you see in the signal flow graph, the GS is the transfer function of the system and node is represented by a circle where axis is the signal that can be either input, output or the intermediate signal of the system. Now, adjacent to line we write the transfer function. So, this is the transfer function of the system, and in case of signal we write the transfer function near to that particular node. Now, the figure which you see below will represent the interconnection of the systems and signals. Now, each signal here is the sum of signals flowing into it. So, if you see this figure and try to find out the value of xs. So, xs will be nothing but R1s into G1s minus, because G2s is having minus sign. So, minus R2s into G2s plus R3s into G3s. So, you will get xs, the value of xs as the summation of all the signals which are coming to the axis. Now, the value of signal C3s, if you are asked to find, C3s will be nothing but xs into minus G6s. So, you will write minus xs into G6s, and xs you have already found, you can put the value of xs and simplify, then you will get the value of signal C3s. So, this signal flow graph property will help in finding out the transfer function of the system more easily. Now, before going into the finding out the transfer function of a system, let us understand few terms which we will use for finding out the transfer function of the system using signal flow graph. First is loop gain. So, loop gain is the product of branch gains found by traversing the path that starts at a node and ends at the same node without passing through any other node more than once and following the direction of the signal flow. So, that means if you are asked to find out the loops will be, first loop you will see as you travel in this fashion. This is one loop where you are starting from the same node and coming back to the same node without tracing the nodes more than once. So, the loop gain of this loop will be G2s into H1s. Similarly, we can find other loops also. One such loop is this one. So, this will become G4s into H2s. Another loop can be this one. So, this will become G4s into G5s into H3s. Similarly, there is another loop which you can trace using this particular section. So, this will become G4s into G6s into H2s. So, G4s into GCs into H3s. So, that is H3s. So, we had G4s, G6s into H3s will be the another loop. So, you see in this particular signal flow graph we have 4 independent loops. Now, let us talk about forward path gain. So, what is forward path gain? Forward path gain is the product of gain found by traversing the path from input node to the output node of the signal flow graph, and that is in the direction of signal flow. So, if you see this particular signal flow graph, there are 2 forward path gains for the particular signal flow graph. What are those forward paths? One such path is the direct path which you can see, which is connecting input to output. So, the gain of that particular forward path is G1s into G2s into G3s into G4s into G5s into G7s. So, this is one straight path. What can be the other path? other path can be the path which is going via G6S. So, you get another forward path gain, that is G1S into G2S into G3S into G4S into G6S into G7S. So, you will get two forward path gains with respect to the signal flow graph which we see in this figure. Next is to find out the non-touching loops. So, non-touching loops are the loops that do not have any node in common. So, if you see the previous case, we found 4 loops. Out of that, this loop is the loop which is not connecting to any of the other 3 loops. So, what we can write, that the G2S into H1S, that is the first loop, is not touching other 3 loops. So, those other 3 loops are G4 H2, G4 G5 H3, G4 G6 and H3. So, the combination of these loops will be the non-touching loop gains. So, when you identify non-touching loops, you will be you can easily find out the non-touching loop gains from the non-touching loops taken 2 at a time or 3 or 4 at a time. So, in this particular figure, the product of loop gain, that is G2 and H1, and the loop gain G4 H2 is the non-touching loop gain taken 2 at a time. Similarly, for others also you can write. So, first we will take non-touching loop gain by considering this loop and this loop, then we take the loop gain by taking this loop and the other loop, and then third one you take this loop and this loop. So, you will have 3 sets of non-touching loop gains where you will take 2 at a time. Now, the product of loop gains, like if you take this loop and this loop, these cannot be considered as a non-touching loop gains because the nodes are common. So, we will only consider the nodes which are not the loops which do not have common nodes for non-touching loop gain. Now, we can also identify that there is no non-touching loop gains where we can take 3 loops at a time, because we cannot find out 3 non-touching loops which do not have the common nodes. So, we will have only 2 non-touching loop gains, means when we take 2 loops at a time, then only we will have non-touching loop gains. Now, let us talk about the Manson's rule, which is important to find out the transfer function of the system. Generally, the block diagram reduction requires the successive application of fundamental relationships in order to arrive at the system transfer function. This is what we have seen in case of block diagram, where we have to apply the fundamental relationships to come at the final transfer function of the system. Now, with the help of Manson's rule, we can utilize the rule to reduce the signal flow graph to a particular transfer function which can relate output to input, and this require only one single formula to convert signal flow graph into the transfer function, and this formula was derived by S.J. Manson when he related the signal flow graph to the simultaneous equations that can be written from the graph. Now, it has complexity involved when you have multiple non-touching loops. So, if you have larger number of non-touching loops, the complexity of the formula will increase. So, this we can understand when we see the formula which was given by Manson. So, many system generally we do not have the non touching loops. So, in that way this will be very easy to find the transfer function. So, generally when you have no non touching loop or only few non touching loops, you can utilize the Mason's formula easily to find out the transfer function. So, let us see what was the Mason's rule. So, suppose if Cs is the output and Rs is the input Laplace transforms. So, the transfer function of the system can be represented as Cs upon Rs, which can be provided with the help of Mason's rule as sigma k T k delta k by delta. So, sigma is nothing but the summation symbol, k is the number of forward paths in the signal flow graph, T k is the particular the kth forward path gain, and what is delta? Delta is 1 minus summation of loop gains, that is individual loop gains, plus summation of non touching loop gains when you take 2 at a time, minus non touching loop gains taken 3 at a time, we take the summation of that also, plus summation of non touching loop gains taken 4 at a time, and so on. So, delta will give you the loop gains related to individual loop gains as well as the non touching loop gains when you take 2 at a time or 3 or 4 and so on at a time. Now, what is delta k? Delta k is the delta for that part of the signal flow graph which is non touching with the kth forward path. So, we close our discussion at this point of time and we will continue tomorrow. Thank you.